Okay, so today is the lecture number 5, and we continue the introduction to quantum. And the postulate number 8 that we discussed today is the time evolution of a quantum system. Okay, quantum evolution of a quantum system. So we mentioned many times that the state of a quantum system is given by psi vector in the Hilbert space. Okay, and when quantum system evolves, changes over time, this vector changes because the state of the system changes, so the corresponding vector also changes, and this change of the vector, what it could be, it can be the change of the length of the vector and the rotation of the vector. Okay, and all these operations are described by so-called Schrodinger equation. Schrodinger equation. So let me write this down like this. So the time evolution of a quantum system is governed by the Schrodinger equation. Schrodinger equation. So Schrodinger postulated his equation from some basic principles, but essentially it was a kind of prediction or postulation. And then this equation was tested in billions of different situations and experiments, etc. And as we know, this equation works like extremely precisely, very well when we describe quantum systems. So, and for this reason, this Schrodinger equation is considered as one of the fundamental physical, one of the fundamental physical equations. Okay, so it states, so this Schrodinger equation is I, which is imaginary unit, times h bar, okay, because we're talking about quantum, and then d over dt, so the time derivative of the state psi. Okay, so this is the state that just represents the state of a quantum system, and it's equal to the h operator, which is Hamiltonian, multiplied by sigma state. Okay, so this is the main equation of quantum mechanics and quantum in general. Okay, so here psi is the quantum state. H operator is the Hamiltonian is operator of energy. Okay, and yeah, so I is the square root of -1. Okay, so this equation is written for the ket vector I, and we can of course write the same but for the vector bra. What we need to do, we need to take the Hermitian conjugation. Okay, and after this Hermitian conjugation we replace ket vector by bra vector, and I by minus I, right? This complex conjugation. H dagger equal to H because Hamiltonian is Hermitian operator, and psi is to be replaced by psi, ket replaced by bra. Okay, so and the resulting equation will be minus I H bar d over dt psi equals to H psi. Okay, so this is the same Schrodinger equation, but written for the dual vector psi, for the bra vector. Okay. So when we talking about Hamiltonian is the operator of energy. Operator of energy. Okay, operator of energy, and if you recall from the classical physics, in classical energy of, for example, of a particle in some potential field is given by the kinetic energy, right? Kinetic energy plus potential energy. And for one single particle in a potential is given by the square of momentum square over 2m. M is the mass of the particle plus potential itself, which can be the function of coordinate, and of course it can be also a function of time. For example, a particle in a gravitational, in the gravity field, it will depend on the distance from particle, like any object, comparing to the Earth, if you're talking about the gravity of Earth, but it's not gonna depend on time, right? If you're talking about some electric field that depends on time, then this V gonna be the potential of electric field or electromagnetic field. Yeah, so this is the energy of a classical particle in a field V. Okay, and in quantum, this energy is promoted to the operator H. So let's put Q. So it's quantum. Okay, and what we do, we simply replace the momentum by its operator. So it's operator P squared over 2m. Okay, and plus V. V is a function of R, and in the coordinate representation, V operator V is given by the function itself. Okay, and as we defined when last week or 2 weeks ago, the operator of momentum is given by minus I h bar nabla, right? And I remind you that nabla is I d over dx plus j d over dy plus k d over dz. Okay, and nabla squared is given by d2 over dx squared plus d2 over dy2 plus d2 over dz2, right? So since the square of pi is given by minus h bar squared nabla squared, the operator Hamiltonian is equal to minus h bar square over 2m nabla squared. Nabla squared is also known as Laplacian and defined and denoted by this triangle. Laplacian plus v, and can depend on r and t. So this is the Hamiltonian for a particle in a field v. And if we have a system of many particles, what we have to do, we just need to sum up all these contributions from every single particle and also take into account possible interaction between the particles, etc. But for one particle, this Hamiltonian is looks like this. And now we can plug in this Hamiltonian to the Schrodinger equation. Okay, and what we're gonna get? We're gonna get I h bar d over dt state psi. Okay, and on the right side is gonna be h times psi, right? And for this h, for the Hamiltonian, we have this one above, minus h bar squared over 2m Laplacian psi, okay? And then plus v depending on r and t psi, okay? So you probably saw this equation already in some textbooks, so because it's a classical textbook Schrodinger equation. Schrodinger equation. Textbook Schrodinger equation. All right, so in this form, this equation is kind of difficult to solve, and we're gonna consider one example which is of particular importance. Okay, so let's consider example 1, and name this example stationary state. Stationary state. Okay. So for the stationary state, what it means? It means that the Hamiltonian doesn't depend on time. So it can depend on r, but no dependence on time. Okay, no time dependence. So in this case, writing down the Schrodinger equation, and for now I'm gonna use the classical psi state representation without cat and bra notation, because in this case it's more tidy. Okay, so let's write it like this. So this is psi, our psi state, but without the Dirac notation, equal to h Hamiltonian function of r state psi. Okay, so now this Hamiltonian doesn't depend on time. I mean, we assume that. And we can try to find the solution that is the the product of two contributions, one from the special dependence on R, and the second one is dependence on time. Okay, even though the Hamiltonian doesn't depend on time, the psi state of course depends on time. So we look for the solution as a product of two contributions from R, special distribution, and T, time distribution. Okay, so we plug in this ansatz to the Schrodinger equation, and so the time derivative, we can take phi r from the time derivative, and here we get time derivative of kappa. Okay, and the Hamiltonian, it can be, I mean, this operator can be very different, but now it doesn't depend on time, which means that it acts only on the special component of the psi state. So now we can take this kappa, which is function of time only, and keep, and our h now acts on the phi. Okay, so now what I do, I can multiply both parts by 1 over k kappa phi. Okay, so I get I h bar phi d over dt kappa over k phi k h phi over k phi. Okay, so now this kappa here cancel down, phi here cancel down, and what I get one part is I h bar 1 over k d k over dt equal to 1 over phi h phi. Okay, so now I notice that this part on the left depends only on t, right? No function that depends on r. Likewise, on the right side, this function, this construction depends only on r and no dependence on t. So one function depending on t is equal to another function that depends on r. That can be possible only if the both parts equal to some constant. Okay, equal to some constant. And now we can go ahead and solve these two equations. Let's start from the kappa. So we have, for the kappa, I have IH 1 over kappa d kappa dt equals to constant. Okay, I can multiply by kappa both parts and get IH d kappa dt equal to constant times kappa. Okay, and so I noticed that I take the time derivative of kappa and get kappa itself times some constant, and it reminds me the time derivative, or I mean any derivative of exponential function, right? So I can make an ansatz and search for the kappa, this function a, some amplitude, times e to the power of alpha and t, right? So alpha and a are two parameters to be determined. So I plug in this ansatz to the equation. I get I h bar, taking derivative of kappa gives me a E alpha t times alpha, right, is equal to constant A E alpha t. So now I can cancel A E alpha t on both sides, and what I gonna get is the value of this constant. The value of the constant is I h bar alpha. I h bar alpha. So this is my alpha alpha that comes from this equation. Okay, so now I consider the second one, 1 over phi Hamiltonian phi is equal to constant, which is I h bar alpha now. Okay, I multiply both parts by phi, and I get Hamiltonian phi equal to I h bar alpha phi. And this is the eigenstate and eigenvalue problem for the Hamiltonian H, right? So if I write this in a general form, it would be something like Hamiltonian times psi equal to energy, because the Hamiltonian is the operator of energy. So the eigenvalues are energy values times psi, right? So I compare the both and notice that energy, this eigenvalues in this case for our equation is I h bar alpha. Okay. So I still don't know this alpha, but I now can retrieve this alpha from this equation, so which is given by minus I E over H, right? I divide both parts by I H bar, and imaginary unit goes to the numerator with minus. So this is my alpha, okay, and the resulting solution for kappa is A, which is amplitude e to the power of minus I e over h bar times t. Okay, so this is the first part of the solution. Yeah, so let me summarize this. So in the stationary state, when Hamiltonian doesn't depend on time, right? The solution of the Schrodinger equation, this one, is the psi, depending on R and T, of course, and it's given by the product of the special distribution, the amplitude, of course, some special distribution that depends on R and no dependence on T, and multiply by this exponential function, which is minus I e over h t. Okay, and here E is the energy. Phi r is the coordinate part of the psi vector of the psi function. Coordinate part of psi. And usually this E energy over h bar is denoted by omega and called by frequency, right? So it's a frequency. So the energy in this case equal to h bar omega. This is famous Planck's formula. So the quantum mechanics appeared when Planck was, tried to describe the black body radiation, and he only could describe it by introducing the fact that, or by assumption that the energy is emitted by portions, portion by portion, and these portions of energy, these quanta, are assigned to have the energy h bar omega. Okay, so this energy of one quanta. All right. So for this solution here, this is the steady state or stationary state solution to Schrodinger equation, which is much easier to solve because we can solve only the only the coordinate part of the Schrodinger equation, and then multiply by this exponential function. Okay, but what is probability? So suppose we solve the Schrodinger equation, found this phi and kappa, and what is the probability? Because the probability is the only thing we can measure in experiment, right? So the probability is given by the absolute value of psi squared, right? And in our case, in general, it's a psi times psi complex conjugated, and in our case, it is a phi e to the power of minus I omega t times a complex phi complex e to the power of plus e omega t, right? So plus omega t minus omega t cancel out, and we get a phi modulus squared. So in stationary state, the state doesn't depend, the probability doesn't depend on time. So no dependence of probability on time. So probability doesn't depend on time in the stationary state. Okay, so this is what we mean when we discuss, for example, the hydrogen atom, right? For example, hydrogen atom, we write down the Hamiltonian for the electron in the Coulomb field of the nuclei of the proton, and it's pretty, that's solvable problem that can be solved analytically. And since this Coulomb potential doesn't depend on time, we write down the stationary Schrodinger equation, solve it, get the eigenvalues of the hydrogen atom, and these eigenvalues, they are basically the energy states of the hydrogen atom. Okay, and the eigenstates, they represent the electronic clouds around the hydrogen atom. Okay, and in chemistry, for example, we denoted them by S, P, D, orbitals, etc. So at this point, quantum mechanics helps chemistry to basically understand the things. But what we're gonna do, sorry, what we're gonna do now, we're gonna consider, so it was example 1. Let's consider example 2. Let's consider example 2. And quite important one. Let's name it particle in a infinitely deep potential well. Particle in a infinitely deep potential well. Or infinite square well. Right, so it's a classical quantum problem which has some, well, good consequences, or so there is something to discuss here. So that's why I decided to bring this problem here. And also this problem is a good practice to for using Schrodinger equation. Okay, so what is infinitely deep potential well? Okay, so we consider a potential distribution on one coordinate x. Okay, and suppose this is potential u, or how we denote it, v. So v potential. Okay, and this is the 0, and we suppose that the well has the width a. It's a here. Okay, it's the second wall of this well, and we assume that this potential goes up to infinity. So this well is infinitely deep. Okay, infinity here, infinity here. So these areas here and here, the particle not allowed to go there because the potential is infinitely deep. Okay, and at the same time, potential is 0 inside of this well. 0 here. So it's pretty straightforward problem to solve. And the procedure is like this. So first we have to write down the Hamiltonian for this problem, which is minus h bar over 2m Laplacian plus u, which is function of x, and which function of x, no dependence on t, and the problem is one-dimensional. So instead of r, we use x. Okay. So now for this potential, what we have? We have 0 if the particle is inside of this well. So it's for x from 0 to a. Okay, and infinity if otherwise. Okay. So u or v, right? We use v here. So v doesn't depend on t. Hence, we can write down the stationary Schrodinger equation, which is h phi equal to e phi. Okay, and solve this as a eigenstate and eigenvalue problem. Okay, so we use this Hamiltonian above, right? So it's gonna be minus h bar over 2m Laplacian. So Laplacian is equal to d2 over dx2 plus d2 over dy2 plus d2 over dz2. But in our case, since we have only x coordinate, the Laplacian in our case will be d2 over dx2, right? So we can use this fact right now. d2 over dx2 phi depending on x plus v phi x equals to energy phi x. Okay, so this is the equation that we are supposed to solve, and we will solve it inside. I mean, typically you need to solve this in different areas. For example, in this area 1, area 2, and area 3, and then connect the solutions on the boundaries. But now, since the particle not allowed to go to area 1 and 3, we can only solve this equation in the area 2, and in area 2 inside. Let's write this down. So outside of the well, right? Outside of the well, which is phi when x less than 0 and when x more than a is equal to 0. So no particles there and no probability to the 0 probability to go outside from the well. So no particle is not allowed to escape from the well. Okay, so inside. So the inside the potential is equal to 0, and this equation is simplified even further. So we're gonna get minus h bar squared over 2m d2f over dx2 equal to ef phi, sorry. Okay, so let me multiply both parts by minus 2m over h bar squared, right? And I'm gonna get d2 phi dx2 equal to minus 2m e over h bar squared times phi, of course, right? So some of you already recognize this equation. It was, I mean, in the previous courses, it might be something like this, minus k phi, right? So the standing wave equation or Helmholtz equation, different names. But typically, how we solve this equation as a combination of sine and cosine function with different of different amplitudes. Okay, so since this is the standing wave, it's gonna be the superposition of two waves with different phase and different amplitudes. Anyway, so we can make this ansatz and find or look for the solution in this way. So a some amplitude times sine some kx, okay, and plus b cosine kx. Okay, sine and cosine. And now we plug in this solution, this probing solution, these answers to the equation above. To do so, we need to find the first derivative by x. So it's going to be a cosine kx times k, and then minus b sine kx times x, okay. And finally the second derivative of phi by x is gonna be a k squared minus, of course, sine kx minus b k squared cosine kx, or taking minus k squared out from parentheses, I get a sine kx plus b cosine kx, which is perfectly equal to initial ansatz. So it's gonna be minus k squared phi, right? Okay, so now we can go ahead and plug in this to the equation, and we're gonna get minus k squared phi equal to minus 2m e h bar phi. Okay, so since now k just multiplies by phi, we can, and this is solution for any non-zero phi, we can divide both parts by phi, and we get and by minus 1. So we get kappa k. K is equal to square root of 1 over h bar square root of 2m e, right? So this is the formula for this k number, and also for the energy, right? So the energy is equal to h bar squared k squared over 2m. Okay, so this is the formula for the energy. So we notice that energy and wave number k, they connected to each other, and this connection, by the way, this dependence of energy by k and vice versa is the dispersion relation. So it's called dispersion relation. Dispersion relation. So anytime when energy depends on k is the dispersion relation. Anyway, so let us define now, is k and energy any number or not? Okay. So how we do so? So we know that wave, this phi at the boundary is supposed to be equal to 0, because outside is 0. That means it must turn to 0 at the boundary, right? So phi at the first boundary is equal to 0, but on the other hand, it's equal to a sine 0 plus b cosine 0, right? So sine 0 is always 0. Cosine 0 is 1, so it's gonna be equal to b, right? So equal to b. So b equal So we conclude that B is equal to 0. Okay, we don't need this B anymore. So for the similarly for the second wall, which has the coordinate A, right? It's gonna be equal to A sine K times A, and it's also equal to 0 because of the boundary conditions. Okay, so for for any for the non-zero A, we conclude that sine Ka is equal to 0. Okay, which means that K times A is to be equal to pi times n, because for any n integer, a positive integer, like 1 pi, 2 pi, 3 pi, sine is always equal to 0. Okay, so we conclude that K is equal to pi n over A. On the other hand, since K is equal to 1 over h bar square root of 2me energy, our dispersion relation, right? Hence, pi n over A equal to 1 over h bar square root of 2me. Okay. Oh, we can use this one actually, this equation for the energy. So since energy is equal to h bar square k square over 2m, we plug in this solution here to this formula, and we get this result. E is equal to h bar squared, then pi squared n squared over 2m I with a squared. Looks good. And now, since this energy depends on n, which is integer number, like any integer number, I'm gonna put this n here to denote this fact that energy now depends on n. Okay, so this is pretty interesting result, and this is basically the fact that energy is quantized in the potential well, right? Because if I take the energy for the first state, it's equal to h bar squared pi squared over 2m I squared, and the energy for any state n is given by E, the energy of the first state, times n squared. Okay, so if I draw this like this, so this is the energy, right? Energy n. The first state is gonna be, for example, here. So this is the E1, and then the second state is gonna be 4 times larger than the first one. So this is the second state, E2, and the third state is somewhere here, for example. So it's E3, etc. So it's a infinite spectrum of discrete states of energy. So the energy is discretized. So the energy is quantized. For this reason, I mean, this word quantum, right? Quantum physics is basically physics of systems that have observable which are quantized, and that's it. So the energy is quantized, and in reality, of course, it cannot go like forever for n to be equal to 100 or 1000, because the energy will be too large. So any potential in reality is a finite. Okay, but there are some real structures. For example, a quantum dot. Let me draw this system like this. So it's a quantum dot QD quantum dot. So quantum dot is just a small piece of matter, like a small piece of semiconductor, like silicon, like germanium, just a small island or small particle. Okay, and then when we have, for example, an electron around, it can come and come inside of this quantum dot and become trapped by this quantum dot, because it needs some energy for this electron to escape out. Okay, so in reality it will be like potential like this. Okay, and and of course in the steady state, this electron will be somewhere around, close to the very to the very first allowed quantum state. So when the electron comes to this quantum dot, its spectrum becomes quantized. In the free space, electron can have any energy, okay, like any energy, any number. But when it is trapped by a quantum dot, the energy of the electron becomes quantized. So it can have some allowed energy states. Okay, allowed energy states. And yeah, and even though this this quantum dot doesn't have infinite energy, right? So this energy, this escape energy for the electron to leave the quantum dot is not infinite anymore. It's a finite number, but it still can be a few electron volts. Okay, so this system can be quite robust. So it's typically it can be like 1 to 10 electron volts. And the point is that when the quantum dot is traps the electron, now it behaves as an atom. For example, it can capture a photon. The photon can increase this. It can cause the electron transit to the excited state, for example, and then when electron transit down to the ground state, it can re-emit the photon. So it behaves as a like quantum source or light source. Yeah, and of course, in the literature there is a solution for the finite quantum well, and I refer those of you who might be interested in to the textbooks on quantum physics. But what I wanted to what I also have to, yeah, of course, the psi vector, right? The wave vector. Oh, sorry, wave vector. The phi, the state, the eigen states of the system. So we found that the come on. The eigenstates of our system is given by this amplitude A, then sine kx, and k is pi n over a x. All right. And for the absolute value squared of this wave function, we get a squared sine pi n a x squared, right? Because a and well, it's better to put modulus squared for the a because it still can be potentially complex. Okay, and for the normalization, I need to integrate this probability over the all x, right, and normalize it to 1. Okay, so we're gonna get modulus squared a integral of sine pn over ax squared dx from 0 to a. And so this integral, it's known fact, it's equal to a over 2. And by normalization, we require this integral to be equal to 1. So we can use this probability, this quantity as a probability to describe our system. Okay, so we conclude that the modulus squared a capital times a small over 2 is equal to 1, and hence a is equal to square root of 2 over a. Okay, so finally the eigenstate in this system is given by phi function of x is equal to square root of 2 over a sine pi n over ax. Okay, so this is the probability amplitude for the particle inside of this quantum well, and we can even draw the distribution, probability distribution inside of this quantum well. Right. So it's 0. This is a. So by the way, in the literature, in the textbook, sometimes the authors put the 0 like in the middle here, and then the result will be the combination of sine and cosine, and discretized by parity, right? By parity of distribution according to this new center of coordinate system. In our case, we put the center of coordinate system on here at the first wall. So our solution is just sine. Okay, so now what I do, I want to plot schematically the modulus of phi. For example, the first one is phi 1. Okay, let's plot it in red. So it's gonna be just 1 half of the sine. So it's like this. right? So it's modulus of phi. So for the second state, is gonna be 0 somewhere here. So it's equal to, it means look like this. So this is the state phi 2. And next we can also draw the state number 3. It's gonna have 0 here and then here. So it's gonna be something like this, etc. Yeah, so as you can see, even in such a simple problem, the energy is quantized and the particle is distributed inside of this quantum well. For example, if you measure the particle, if you do the measurement and trying to find the particle, for example, at this point, okay, so in this point, you cannot find the particle in the state free, because it gets 0 probability there. So the particle cannot be observed in that point. At the same time, the particle in the state 2 most likely to be observed in that point because it gets the probability maximum in that point. Likewise, for example, in this one, you cannot observe the particle in the state 2, but the particle in the state 3 and the state 1 have a large probability to be found there. It is the same particle. The only difference is the level of energy. Like ground state is the state 1, and the particle is distributed like this red distribution. But if I excite the particle somehow, for example, I send a photon there, the particle absorbs the photon and jumps to the state 2. So now it changes the probability distribution, and it's like redistributed within this well, and changes the the position, the average position, etc. So in this sense, the particle doesn't behave as a particle, right? It behaves as a wave. Hence this particle wave duality. Okay. And another point to mention here, if you look at this formula, so we notice that energy is actually depends on the size. For example, when we're talking about the finite quantum well, which is quantum dot, right? So this is the A, characteristic size of the quantum dot. And we see that if we make this size like very large, then the energy will be very small, and the separation between the energy levels will be also very small, and this quantization is gone. So for the large object, for the large system, the quantization does not manifest itself. Okay, but if we make this area smaller and smaller, we start observing the separation, the discretization between the energy states, and also the energy of the first state will become larger. Okay, so if we reduce the size of the well, it's like smaller structure, the energy goes up, so energy gets increased. Okay, now, for example, you can take a quantum well, put a electron there, electron gets some energy, and then you can try to squeeze the quantum well, okay? And you know that if you squeeze it, the electron acquires some extra energy because of that. And of course, the same is required by the energy conservation law, because you do some work, right? Squeezing the walls, and that work is spent for the electron to go up in energy. All right, so this is the postulate number 8, and we transit to the postulate number 9. So do you have any questions about this part? If not, let's transit to the postulate number 9. And this is about mixed states and their description. Mixed states. So let's formulate this way. Mixed states are described by density operator. Are described by density operator. Density operator. Pretty important one. So let me even maybe color this one like this. All right, so density operator and why we need it. So as we have been discussing over 4 lectures already, or 5 lectures, a system in a pure state is given by a superposition over the basis vectors, right? For example, state psi, we can write this as a superposition of state C, the coefficient C0, state 0 plus state C1, 1 plus etc. So if you take into account other levels, it's going to be other terms in this summation. So it is a system in a pure state. So what it means to have a system in a pure state? A pure state means that a system is described by only one psi vector. Okay, so it's gonna be just one psi vector. However, the description by just one psi vector is impossible in some cases, and some important cases. Okay, so for example, let us write down the however, or the description by just one psi is impossible in a number of important cases. The cases are so important that you almost never meet the description by psi. You actually, like when you read papers, books about quantum computing, usually the results are represented in terms of density operator, and we're gonna discuss what it is. All right, so the important cases. One case is, for example, an ensemble of an ensemble of quantum systems. An ensemble of quantum systems. So let us consider an array or a group of quantum systems. They can be isolated, not interacting, and each quantum system gets its own quantum state. Okay, psi1, psi2, can be psi3, psi4, etc., psi-n. Okay, and each of these states, each of them, for example, psi-n, can be represented using this this representation, right? This Cn, the series Cn times state n, for example. That's not good notation. Let's put I here. Okay, so any state psi I is given by the superposition of the basis states. But of course, since the systems are different, the psi-n, psi1, psi2, psi-n, etc., they are different. Okay, and if we make a experiment and blindly pick up one system in this ensemble, okay, and we measure it, we can find this system to be in a state, for example, state I. Then I put this system back, do the measurement again, and find another system in, for example, in another state. Okay, and I do this measurement multiple times, and after that I can derive the probability, like classical probability, of finding a system in a particular state. And let's denote this probability by the pi. Okay, so pi is the probability that system I is in the state psi I. Okay, and since this is probability, we normalize the probability to be 1, right? So if I sum up over all possible states, all possible realizations, the result is 1. Of course, in reality, we never do this measurement, right? So like usually this probability comes from some assumptions. For example, I mean, one example could be Maxwell distribution over the velocities, right? For example, if you have a like electron source that emits electrons, it can be just a heated piece of metal, okay, upon some temperature. So this source emits electrons, and you roughly know the energy of these electrons, but the velocity of these electrons distributed over some average value, okay, or momentum of these electrons distributed somehow. And if you measure this electrons momentum, for example, of this one, you get some value. You measure this one, you get another value. You measure the third one, you get yet another value. And then you can plot this distribution of the electrons over the momentum, okay. And of course, each electron by itself is the quantum system, okay, and it's described by psi state, okay, but you don't know in which momentum you will absorb this electron when you measure it. So so there is a there are two probabilities here. One probability is purely quantum probability associated with the statistical nature, statistical property of the quantum of this psi vector, okay. But there is a classical probability which is associated with the fact that we cannot predict in which, with what momentum or velocity the electron is emitted from the source, or in which direction it's emitted, etc. So there are two probabilities here, and this P takes into account this classical probability. Okay, so this is the first case when we cannot use only one psi vector, because obviously if you have multiple systems and each one described by psi, but there is a probability distribution over, like this classical probability distribution over the particles, we have to take into account all the realizations. So we need to average the things also by using the classical probability distribution. Okay, so in this case, only one psi vector is not sufficient to describe the system. And another example of systems or cases when having just one psi vector is not sufficient is a subsystem of a bigger system. A subsystem of a bigger one. Okay, what is this about? It is about, so suppose we have a bigger system, like many quantum particles there or whatever, any like sufficiently big system. And if we consider two subsystems of this bigger system, one is A, another one is B, and we want to describe only the state of system A, but it is in interaction with the subsystem B here, right? So they exchange the A energy, interactions, etc. So obviously the state of site A or subsystem A will depend on the parameters and the state of the subsystem B. Okay, so again, in this case, it's not enough to have just one psi vector to describe this to this case. And this is important case because this subsystem A can be, for example, our quantum dot we just discussed, right? Like a small piece of matter that can capture one electron. Okay, so it's a quantum system, but of course, around this quantum dot we have the rest of the world, right? The measuring equipment, the everything is around, and everything can affect this quantum dot state. Okay, so there is a action on this quantum dot. In this case, we call this system is a open system. Open. Of course, any system is open, but when we like theoretically describe, we can sometimes we can omit this for simplicity. We can omit this interaction of the system with the rest of the world, but in other cases, this interaction with the environment can be crucially important. Right. So yeah, so this is the second case when the using just one psi vector is not sufficient to describe the quantum system. And in order to be able to describe these cases, we introduce the concept of density operator. So density operator, how we introduce that? Density operator. Density operator. So when we talking about quantum systems, the most important thing is the expectation value, right? Because the expectation value in the end of the day is what we actually measure. So this is how we interact with quantum system, how we interact with it. And the expectation value for any observable A is given by the matrix product, the matrix coefficient psi, which is state, right? Then operator of the observable A operator, times psi ket. And this, of course, holds true for any system, including the two cases that we discussed above, ensemble and open system. Okay. And in this, and of course, each of these psi vectors can be represented as a superposition of a basis vectors, Cn basis vector n. Okay. And I also remind you that when I take the sum of all the diagonal elements of this matrix N, right? Or I mean, in other words, if I take the outer product of n of basis vectors and then sum up all of them, I get the identity matrix or identity operator. Okay. So let's suppose I have an ensemble of quantum systems. So I have in mind this first scenario, first ensemble. Okay, and I do the measurement, and I find, for example, for the expectation value of observable A for the first system to be to be equal to psi 1a psi 1. For the second one, I get psi 2a psi 2. For the third, I would get psi 3a psi 3. Okay, and some of and etc. for all of this. And of course, sometimes some of these results will be equal, which means that the two different subsystems they are in the same state. Sometimes they are different, meaning that they are in a different state. Okay, so let us enumerate the realizations and group up all the realizations with numerating them by the state. So all the realizations of the state 1 will be grouped to the n small 1 times psi 1a psi 1, and I divided by the total number of subsystems n. Okay, so for the second possible state, I have n2 psi 2a psi 2 over n, etc. The n3 and 4 and so on, so that ni over n is the probability pi, probability of state I. State here means in classical meaning or you can say sort, like the probability to observe a system of sort 1, the probability of observing a system of sort 2, etc. So all these systems have the same psi, but classically they are in a different state. Okay, and pi is the probability of finding the system in the state I. Okay, so now if I measure the observable A and take into account this classical probability distribution, I have to write I have to average all these expectation values over the classical probability too. So the total expectation value for the entire system, for this mixed system, is gonna be summation over I, this classical probability pi, and then the expectation values in the quantum sense, psi I, a, psi I. Okay, and now I want to rewrite this expression somewhat, and I'm gonna use this formula here. So identity matrix, expression of identity matrix through the outer product of basis vectors. So I gonna introduce this. No, literally, I mean, I can introduce this identity matrix in any part of this expression because it doesn't affect anything. So I write the summation of over I by pi psi I A, and now I introduce this this summation over here. So it's n n, okay, and summation runs over n, okay, and then psi I vector, okay. So now I can take this summation to the first place. It's gonna be sum over I, sum over n, pi I, sorry, pi, then psi I A, n, psi I state. Okay, so now I can rewrite this in the following way. So first of all, I notice that this ket n bra I is a scalar, and I of course can take this scalar and move it around as I want. So I can rewrite this on the first place here. Okay. So it's gonna be I n summations, then pi pi, then n psi I. This is the term we moved around, and then psi I a n. Okay. Now I can rewrite this in the following way. So I keep this summation over n in the first place, and then move the summation over I close to the index I, and also since this pi is a constant, it's a probability, right? I can introduce it, I can move it here, and this vector, move it here. All right, so it's gonna be a summation over n, then n vector, then summation over I, pi, state psi I, okay, and then operator a, n. Okay, so so here I have this construction, that part that depends only on the probability of the system. So it takes into account the both probabilities, the quantum that comes from the psi and the probability of this classical probability p. Okay, and this is the only part that depends on the index I. So it's natural to introduce the operator rho, okay, and this operator rho is the density operator. So let me write this in color. So the operator rho, which is summation over I, I runs over the different quantum subsystems. Okay, so it's not the quantum state, it is different subsystems, runs over I, in contrast to n, for example. N here is the eigenstates or basis states of the system. So classical probability pi, then psi I. This is the operator, density operator. Density operator. So for the expectation value for the mixed state, we get summation over n, state n, then density operator a or rho, then the operator a, and then n. Okay, or recalling the notation for the trace, right? Trace is the summation of the diagonal elements. So this is exactly summation of the over diagonal elements. So we can write this simply like trace of row A. Okay, so this is another important formula which basically states that in order to find the expectation value for any observable A, we can simply take the trace of the operator A with the density operator. Okay. So in this that means that in order to describe a quantum system, instead of psi vector, you can use density operator. Okay, so let us write this down like knowledge of density operator of a system allows to calculate the expectation of any observable. Knowledge of density operator for a system allows to calculate the expectation value of any observable. Okay, so a pure quantum system is described using psi vector. The mixed quantum system is described by density operator. Let us consider a few properties of density operator. Properties of density operator. So first of all, density operator is Hermitian. Why? Since the density operator is defined by this construction psi I times the classical probability, which doesn't affect anything because that's just number, right? So if you take the Hermitian conjugation, well, there is a property here to remember. Like when you have two matrices A and B, right? And you know, if you take the transpose of this of the product of two matrices, the result is the first matrix, the second matrix transpose times the first matrix transpose. So you not only transpose each matrix, but you also reverse the order of multiplication of the matrices Okay, and since the Hermitian conjugation is complex conjugation and transposition of the matrix, the same applies here. So it's equal to psi I conjugation, Hermitian conjugation dagger times psi I dagger, like this. And now when you take this Hermitian conjugation of each one, you get psi I, which is exactly what you started from. So this is the proof that density operator is a Hermitian operator. Okay, so another property is that the trace of the density operator is equal to 1. It's instructive to prove this one too. So for the density operator, by definition, it's equal to psi I pi, and the summation runs over I. I is the number of the subsystem. Okay. Okay, so so what is trace? The trace is the matrix, the summation over the diagonal matrix elements. So for the single matrix element, diagonal matrix element, we write n row n state, which is summation over I, then n psi I n pi. Okay, and finally for the trace of rho, we have to take a sum over n, right? So it's a sum over n, sum over I. So in contrast to I, n enumerates the quantum states, different quantum states. What we get? We get n psi I n pi. Okay, so now since these two just complex numbers, I can exchange their positions and rewrite this like this: n summation over n, summation over I, then psi I n, then n, then psi I, and then pi. Okay, so now I can sum up all the n states, and this gives me the identity operator, right? So it's equal to sum, an identity operator applied to any vector, it's vector itself. So we omit this identity operator and get the following. So it's a summation over psi I, inner product psi I, the same vector, pi, okay, and summation. So we assume, or I mean, this is the requirement of the quantum mechanics, that the vectors, the state vectors, are unitary normalized. So this inner product gives me 1. And I came to the conclusion that the trace of the density operator is given by the summation of all probabilities pi, which is equal to 1 by definition of probability. Okay, so the trace of the density operator is equal to 1. The next property is that for a pure state, the square of density operator is the density operator itself. For pure state, we have density operator squared is equal to density operator itself. So for the pure state, so for the mixed state, right, we have this summation of the classical probabilities times psi I, and we can use this to describe mixed quantum states, mixed systems. But if we have only one subsystem, then this pi is equal to 1. And I mean, we can simplify this to the pure state. So for the density operator of a pure state, we have simply the outer product of psi times psi. Okay. So that means that using density operator, we can not only describe mixed state, but also the pure state. So the density operator is a much more powerful thing than psi vector. Okay. And now this proof is quite simple, because this squared density operator is just psi times psi, psi times psi. Right. And because the vectors are normalized, this inner product inside is equal to 1. So the result is equal to psi times psi, which is equal to pure state density operator. And finally, for the last property today, without proof, just for completeness, because this one is pretty important. So for the let me actually write this in red. For pure states, the trace of the density operator squared is equal to 1. For mixed states or systems, the trace of squared density operator is less than 1. Okay, and the closer the trace to 1, the more pure quantum system. Okay, so when it's equal to 1, the quantum system is in the pure state, and we can use it. We can use the psi vector to describe the system. But if this is less than 1, then we have to bring this description using the density operator. All right, so unfortunately I was not able to cover everything that I plan to cover for today. So we will conclude next time this introduction to quantum, and also next time we will start with the we will begin discussing the quantum computing, where we will significantly use all these things and concepts. So let me stop the recording and then we can discuss.